Welcome back to ECE 320A. We are reviewing for exam number 4, and we're using an exam from the fall of 2015 to do that review, and we're now at problem number 9 that we're looking at or examining, and it's trying to sketch the magnitude Bode plot or the frequency response magnitude in dB of this particular transfer function h of s. And this transfer function has a couple of zeros, and it actually has 3 poles. So we have a few things to keep track of, but remember the magnitudes, once we find their break frequencies, we don't have to worry about those slopes stopping like we do with the phase. So once we start these slopes, we don't have to worry about, uh-oh, where's that going to turn off? It's going to turn on and stay on throughout the remaining frequency axis as we keep marching to higher and higher frequency values. The first thing that we want to do then is convert this transfer function to pole zero form and then time constant form. Let's identify the zeros. We can find those. We have one at the origin and one at 100. We have a pole at 1. And now we simply need to factor this denominator polynomial, s squared plus 10.01s plus 0.1. And now if we factor that, we actually will see that this is not a quadratic factor. It's actually 2 real factors. We have a factor of s plus 10 and a factor of s plus 0.01. So we have a pole at 0.01 radians per second, and we have another pole at 10, and we also have another pole at 1. So if we were to do all of this factoring, we would then have a 0.1, we have a 0 at the origin, we factor out 100 from the numerator, and we have s over 100 plus 1, and we then have an s plus 1, that's already in time constant form or pole zero form. We then factor out the 10, and we factor out the pole at 0.01, and now we are good to go. We need to find our constant. Our constant is now going to be 0.1 times 100 over 10 times 0.01, and hopefully all of those then end up giving us, here we have a net of a 10, and in fact this 0.1 will cancel one of those, and we have a 0.1, so that, well, we can do it many different ways. We could say that this cancels that, and we have 1 over 0.01, or we have 1 over 10 to the minus 2, or we now have 100 for our gain, which in dB, which is what we want, is our constant is going to be 20 times the log base 10 of 100, or that's 2 times 20 times the log of 10, or that's now 40 dB. And we can now come down here and say, oh, our constant is actually giving us this contribution or component of 40 dB. This is now due to our constant. Now all the other pieces, we have a 0 at the origin, and that's going to now cross 0 dB at 1, so we know where that's crossing the 0 dB, but it's always on, so we go back a decade, 10 to the minus 1, it's down at minus 20. We go back another decade, it's down some more, and I like to just sort of draw these dots so that I can now, and I would recommend you bring a straight edge so that you can quickly draw a more accurate line that represents that 0 at the origin. And now we have one more 0, and sometimes you'll see maybe in the solutions I've written down the word description of this, and I find that very helpful actually. We have one more 0 to take care of, and that breaks at 100. So it's going to be 0 dB until we come to 100, and now it's right here. So this is our 0 at omega equal to 100. We've now accounted for our constant and our 0 factors. We can now start looking at our pole factors. The first pole to occur occurs at 10 to the minus 2, or 0.01. So now it's back here. Let me go ahead and do that in black. It starts there, and it starts going down 20 dB every decade. And so hopefully then I can now get my ruler out and sketch that line. I don't have a ruler, I'm joking, but you can. This is now one of the pole factors. We have another pole factor that breaks at 1, so it's 0 dB until we reach that point. It's not sloping continuously. It starts breaking at 1 and coming down 20 dB per decade. So now we have this contribution, and we have one more pole, and it starts at 10, and it falls off at 20 dB per decade. So here is our pole at 10. Here is our pole at omega equal to 1, and here is our pole at omega equal to 0.01. And we now need to put all of those pieces together. And sometimes I like to just go back far enough in frequency until I don't have any breaking occurring, which there's our sort of our first break. So let me go to the left of that, and if I come back all the way to 10 to the minus 3, I see that my pole at the, I'm sorry, my 0 at the origin is giving me minus 60, and my gain is giving me 40. If I add those up, I should be starting right here at minus 20, but I'm going to be coming up at a slope consistent with that 0 at the origin. Then what happens at 10 to the minus 2 radians per second is I have a plus 20 dB decade, I'm sorry, a plus 20 dB per decade positive and a minus 20 dB per decade negative. So those cancel, and I'm actually flat until I reach a new break. My 0 is still contributing, whoops, and so is that pole at 0.01. The new piece that's coming in is this pole at omega equal to 1. So I now go down to that, and then beyond that value of 10, I'm now sloping down a little bit more, because now I'm sloping down at minus 40 dB per decade until I reach the next new entry into that, which is the 0. But here I go 40 dB per decade down from 10 to 100. So I would not be at minus 40, I should be at minus 60. And finally, I have this 0 coming back up, so I now am not going down at 40 dB per decade, but I'm going only 20 dB per decade, and now I come back, and this final slope that I have, so here is my final curve of magnitude. This slope, that should be a straight line, is the net pole 0 excess times minus 20 dB per decade. I have 3 poles and 2 zeros, so I should be sloping at minus 20 dB per decade beyond a frequency where I last experienced a change, which was that particular frequency of 100. So beyond that, I have a slope of minus 20 dB per decade. Before that, I actually am sloping at minus 40 dB per decade. Between 1 and 10, I'm sloping at minus 20 dB per decade. And before that, I'm flat at 0 dB. And then before 10 to the minus 2, I'm sloping at plus 20 dB per decade. And that is now my magnitude sketch. Obviously, you could do a little bit better with a straight edge than what I've cobbled up here with a hand-drawn straight line. But that's now your magnitude plot for this particular transfer function.